All right, so today we're going to talk about how to solve ice table questions. And there is one of them. Zero point 0.1 mole of hydrogen gas and zero point 0.1 mole of iodine gas were mixed in a 1-liter vessel and heated to 450 Celsius. At equilibrium, concentration of iodine was 0.0213 moles per liter. Calculate the equilibrium concentration of hydrogen gas and hydrogen iodide gas. Well, first of all, I should admit that there's lots and lots of words and feeling, I guess, exhausted from that amount of words and feeling frustrated is fine, is normal. When I read questions like that, I also get frustrated because I don't know what to start with. Well, but I know for sure that your first step should be write out what is given to you. And in this example, you can see that what's given to you, moles, right, of hydrogen gas and iodine gas, which is H2 and I2, right? And so with the same logics, just go over the whole question and you can write out what's given. 1-liter vessel, right? So it's volume. Temperature, honestly, in questions like ice table questions, it's not that important. So I can even cross it out. But remember, only in ice table questions. We have equilibrium concentration, which we're going to talk about a bit later, and why it is important is exactly the word equilibrium. So here's what's given. We have N of H2, right, 0.1 moles, N of I2, 0.1 moles, volume, which is 1 liter, and concentration at the equilibrium. Super important. We have to write this sign down, equilibrium. Now, let's write out the reaction, but balanced reaction. So what do we have? We have hydrogen gas and iodine gas were mixed. So hydrogen gas always goes with H2, right? And we put G. Plus iodine gas, which is also I2, and we put G as a state and heated it. At equilibrium concentration, iodine was calculated the equilibrium concentration of hydrogen gas and hydrogen iodide. That's exactly what we have as a product, which is HI, and it's gas. States are important here. Well, to balance this reaction now, and always check, if you're writing out the reaction, always check the balancing. It will change the whole outcome of the question if you don't balance it correctly or if you don't balance it at all. So I should put 2 here and it seems fine. Yep, it's all good. We should write out ice table. We put ice, the letters under each other. I means initial, C means change, E means equilibrium. And these guys, these letters here, they're talking about concentration. Now, before we even write numbers, let's think about it. Let's think about concentration. Concentration is measured in moles per liter, right? We have some moles per liter, but we're going to talk about them later because they are at the equilibrium, right? That's an important phrase. Now, do we have moles per liter of hydrogen gas and iodine gas? No, we don't, but we have moles and liters. So to find the concentration of the hydrogen gas, we're going to do 0.100 mole over 1 liter. Well, obviously it's going to be 0.100, but now it's going to be moles per liter. You cannot skip this test because some questions can be tricky. There could be 2 liters, right? The answer will be changed. But in this case, it's easy. It's 1. But still, you have to show your work. You have to show your teacher that you understand where the moles per liter come from. You should show your teacher that you understand if there was 2 liters, the answer will be changed. So you have to write out for both of them, for iodine and for hydrogen. So for iodine, it's going to be exactly the same, 0.100 moles over 1 liter, because we use exactly the same volume, 0.100, but now we have moles per liter. Over here, we're getting the units. So what I get here, the concentrations, these are initial. Think about it. This hydrogen gas and iodine gas were mixed, right? So this is the initial concentration. Now I'm going to split this table into 3 parts because we have 3 compounds. Now it's important. In the ice table, we never put solids and we never put liquids. So if you get water, which is liquid, of course, you're not going to put it in the ice table. You just put this kind of like nothing, right? And then you just put numbers over here, here, and here. But since we have gases everywhere, we're good. We can write out everything. So for hydrogen, it was 0.1 from here. So I'm putting 0.100. For iodine, the initial concentration that was mixed in the vessel was also 0.100. And there is no information that we had hydrogen iodide gas. So there was no product in the beginning, right? Imagine if you have tea, right? Hot tea or coffee, whatever you prefer, and you mix it with sugar. Initially, what do you have? Do you have sweet tea right away? There is no originally sweet tea, right? So the sugar, at some point, the sugar was added. So what's happening is that sugar and tea, they're two separate reactants. And if there's two separate reactants, initially they were not mixed. That's why we do not have sweet tea, right? The sweet tea is product. We do not have sweet tea, so it's 0. Now change. Change we assume as X because we don't know how much changed, right? But we know that we had less, if we keep the example with sugar and tea, less sugar, of course. Well, we don't have really less tea, but maybe in the microscopical scale, maybe we do. But anyways, the reactants, we do negative change, right? Because they actually also reduce, right? Because now you're getting sweet tea. And since you're getting sweet tea, you're getting X. But look what you have at the product. Now let's go back to the chemistry, actually. We have 2. So 2 will be put over here. So we have 2X. Now at the equilibrium, you can combine these two. So let's combine them. 0.100 minus X. Same thing for iodine, 0.100 minus X. Now 2X, nothing, right? We have 0. So you can write plus 0, but it really doesn't make sense. They're basically done. Now, why here I highlighted this equilibrium? Because I2, this at the equilibrium was 0.0213. So instead of 0.100 minus X, I can put 0.0213 minus equals to 0.100 minus X. So let's do this. 0.100 minus X equals to exactly what they gave to us. So I didn't really make this number. I just got it from the question. 213. Let's solve for X. This is pure math. So in this case, X will be equal to 0.787. That's our X, right? So, but because these two are the same, this is also going to be 0.0213. So answer for this is already ready. It's 0.0213. But just because they were the same, you can solve the same thing. But well, for hydrogen, for example, you would write exactly the same and you would get exactly the same number. So the concentration will be this. They have equal concentration at the equilibrium. But what about HI? We have 2 times X. We just found X, which is this guy here. So we're going to just multiply it by 2 to find the concentration of HI. So concentration of HI at the equilibrium equals to 2 times 0.0787 will be 0.1574. And of course, we have to put units. So it's moles per liter. And the answer is H of the equilibrium, H2 at the equilibrium will be 0.0213 moles per liter. And concentration of HI at the equilibrium as well, because the initial one was 0, remember the example, was 0.1574 moles per liter. Never forget the units because lots of teachers don't like when the units are missed, and some points can be lost even though you got the correct answer.